Hey, good afternoon, everyone. So this is a seminar related to the CPAMI series of seminar, and it is sponsored by the KW section, the CIS and the CSS chapters. And I would like to welcome today Dr. Faisal Safid, who got his bachelor's degree from University of Sétif in Algeria, and his master's degree from University of Malaya, and his PhD degree from University of Waterloo. So he's one of ours. And he has been since 2006 doing research work, doing research cooperation with a number of institutions. Some of them are in North America, some of them are in the Middle East, and some of them are in Asian countries, such as at some of the institutions in Singapore. Dr. Safir has done a good amount of work in the area of CMOS imaging with application to smart systems, and he's going to tell us today about his experience with a number of topics that he has been investigating over the past few years. So the floor is yours, Dr. Safir.
Thank you so much, Dr. Fatih. Thanks so much for this introduction. I'll try, inshallah, to start this. Is the microphone fine, or should we?
I think it remains that way. The light. Araf, is that the case?
The contrast is not okay.
Yeah. So if you can put the bigger, side.
Yeah.
Yeah. So that's fine. Yeah. This is basically how it remains. Yeah, I like it. Yeah.
So this is the best that it can get. Okay.
Yes.
Great. Let me try this. Okay, great. I have to end right on this. Okay. Thanks so much, Dr. Fakhri, again. Special thanks for this invitation. And today, inshallah, I will try to talk about the intelligence design. And what I mean is, I emphasize on this underlying letters here, that we are not talking about intelligent design. This is totally different stuff. This is in contrast to the evolution theory. We are talking about the intelligence design. So basically, first and foremost, let's define what is that. What is intelligence? Since ages, since before the Greeks, since the Egyptians, and since ever the human starts to think, they discovered that they have some kind of intelligence. But what is it exactly? So many people, they try to come up with a definition. One of them, funny actually, by Socrates, he says that I know that I'm intelligent, so he knows that, his self-awareness, because I know that I know nothing, basically. So that's quite sarcastic statement, but it has lots of meaning, especially self-awareness. And then some of the definitions that are actually contradictory, like Albert Einstein said here. The true sign of intelligence is not knowledge, but imagination. So here, this guy, Socrates, he relates the intelligence to the knowledge, okay? That he knows. He doesn't know. Not like in, that famous guy, who's that? Like Ramsfeld. They know that I know what they know. No, this guy knows that he doesn't know, okay? Here, this guy is not relating intelligence to the knowledge, he's actually relating it to imagination. Again, it's somehow contradictory. To make it even worse, people, they define now different types of intelligence. Some of it is in analytics, some of it in linguistics, like some of the work of Dr. Fakhri, some of them emotional. Very hot topics in intelligence, actually. And actually, some psychologists and neuroscientists who are studying intelligence, they said that they don't have hard evidence of the interconnectivity between these different types of intelligence. It's really complicated stuff. So the bottom line is that there is no consensus on what constitutes intelligence. Before I forget, what is that? Okay. All right. I hope that to finish this within half an hour. So please remind me. Okay. So my view, it's just a view. I don't say that this is the right one, but this is my observation. So I have 4 points. Unfortunately, it's cut here. I will try to discuss it even though. So the first point in the intelligence definition, what I think it is a faculty, it's a talent, it is an aptitude, something that gets built into our system, our being. In Arabic, malaka, something given. Something given. We don't know where or how it comes. And it's inherently found in humans, animals, and even in physical systems, by the way. In physical systems. In physics, basically, in physics law. Okay? And it's surmised responsible means it's inherently or deducibly responsible of problem solving, especially in solving problems, capabilities, and that's related to the neural network to some extent. The second point of intelligence, I see it, is basically the integration of functionality. So the brain, for example, is capable of sensing stuff, seeing, hearing, etc. Everything is in the brain, right? You sense through the brain. That's how it comes. Not only sensing, you control also the muscles through the brain, the neural system. Not only that, to make it even more complicated, there's a feedback thing and signal processing that the brain can do. That's also related to the brain. So there is a kind of functionality integration, and that's where the intelligence is coming on. And if you want an example, the iPhone actually. The I is actually for intelligence. Because the iPhone now is integrating many functionalities. Music, video, phone, etc., etc. It becomes what? It becomes smartphone. So the functionality integration is in itself a reflection of intelligence. You can do many things using one single stuff. And another point I would like to emphasize here on among these functionalities is the extraction of ideas and knowledge. From where? From the physical world. And that's how the origin of math. Circle, for example. An example. Circle is from the observation of human being of the nature. Okay? There comes a circle. Okay? So the extraction of abstract things, it's one of the capabilities of this intelligence, or reflection of this intelligence. Okay, the third point of the intelligence is basically the know-how, the how it's made. If you are following Discovery Channel, I always watch that. Is the how it's made stratagem. Stratagem is basically composed of two words, strata and gem. Gem is the, gems, right? Basically, it's the master plan, or the plan of action. Basically, how you can do things in a planned way, and basically how to solve problems in a systematic way. Okay, this is also one of the reflections of the intelligence. Okay, and basically this is related to the intelligent design. How or intelligence design? Actually, this is in particular is related to intelligent design, not intelligence design, because this is actually related to this versus the evolution thing. Okay, we'll come to this point later on. Actually, the last is not shown in there, which is the last thing, and thank God that's not shown here, is the intelligence. I also stands for the middle letter in CIA, is to extract information. Extract information to know what's going on around you. And that's what the intelligence also in security domain means, is to extract information to know what's going on, just from observing stuff. Okay, so these are various reflection of intelligence that attracted my attention. Now to the physical world. This guy, also from Greek civilization, Aristotle, says a very, very astonishing statement. Nature does nothing uselessly. There's no useless thing in nature. Everything has a purpose, everything has what? A reason. Okay? So this statement and this statement is also another important statement by this guy, who is that? Kepler? No. Carl Sagan, who wrote this about Kepler, yes? Kepler said that. Said the diversity of phenomena of nature is so great and the treasures hidden in the heavens so rich precisely in order that the human mind shall never be lacking in fresh nourishment. Intelligence. Huge. Lots of ideas in the universe. We'll see some of them in this presentation. Alright, good. Being inspired by those two statements, I link two things actually. I link this point, which is basically the inspiration of the intelligence of the biological and physical world, and especially the biological system, which has learned over a long period of time, if you can call it evolution time, basically testing many things and learning from the universe, and basically learning from the multifaceted, challenging environment, okay, that the biological system is facing. So, inspired by this intelligent design, and also inspired by the multifaceted challenges of the engineering tasks. Engineering, like for example design, has multifaceted problem to solve. Okay. So because has a solution and this has a problem, why not taking them and make a biomimicry solutions for the different challenging systems? Especially here, the application would be for biological vision. So what I say here is that the biomimicry of biological system intelligence and its implementation into smart electronic system, okay, in circuits and device level, will allow us to do a design of intelligence. And the application that we choose is smart CMOS imaging. We will get to that in a second. So before getting deep into that and to the implementation, let's have a look just very quickly on the standard imaging or electronic imaging system. So this is the standard system, okay? I don't want really to get you into the details, because it's more specific there. So you have a scene that you need to image, okay? You have a lens through which you focus. You have the micro lenses and the color filters and the signal converter from light to electrons and stuff like that. Then you digitize it, you color process it, and then enhance it, and there you go. You have a picture in less than a second. So this is basically the anatomy, if you would say, of standard electronic system. Oops. Okay, so these are the description. Okay. So the image sensor is actually the core of this. That's where the electronics is playing a big time. It plays also some aspect in here, but really at the software level when we reach this stage. But at the electrical level, and there where the application we are talking about, there we are going to discuss. Okay. All right. So all right. Forward to the anatomy. If you open your camera, that's what you typically would say. You will see an array, okay, of sensors, basically photodiodes with transistors in every single pixel of them, which is a picture cell. Okay, you will find some electronics around that will control the time and the signal acquired or to be acquired from these sensors, and you will find some processing circuitry that will take the signal coming from each row of these and making some kind of processing like color processing and noise reduction, for example, to get, and also amplifying the signal to get the data out, including also the A to D converters as well. So this is basically a description of the CMOS image sensor. Now, philosophical statement. We start from philosophy, now we want to implement, being inspired by biology, we want to implement the intelligence. Now the first statement is this one. The image scanning. What I said here basically is that the image scanning in terms of display is actually raster. Okay? It's raster scan. The scan for acquiring the image is not necessarily have to be the same as the display scan. So the image scan is basically how you read pixel by pixel the image array. Okay? Or in the display domain, how you display pixel per pixel. Okay? So I said that the image information acquisition is the priority of the imager. We don't care about the display because we want to acquire the image. Now, this is statement number one. Statement number two, when we acquire the image, I'm not going to read that. When we acquire the image, even human attention is not the same over the whole area. I'm focusing only on where the optical axis is, but the surrounding I'm taking subsample information. So that's what the human visual system is telling me, and we'll get to that in a second. So only region of interest, or ROI, or ROI in French, which is a king, are sampled at the highest imaging requirement and dynamic range and spatial resolution. So only the area of interest should be acquired with the maximum resources. The rest with minimum resources. And we'll get to that in a second. And that takes us to a very important concept, and that is the fovea. The fovea, we'll get into it in the next slide. So, is basically how the image is sampled in the human eye. It's part of the human eye where the resolution is the highest and is the best in color resolution. Okay. So we want to implement this particular architecture of the retina. We'll get that in a second. In fact, we will try to implement this, being this, the intelligence of the human visual system or biological imaging. We'll try to implement it in two different ways, actually 3 different ways. So the first one is that we want to basically, as I said, we want to limit our resources, memory, processing power, and time, basically speed, to only this area of fovea in the image sensor. Okay, and of course, not all image area are the same as I said. For example, you have the foreground, you have the background, you have the region of interest. So each one of them is not at the same level of importance, so it should not be acquired at the same level of cost. Okay, so that's the idea. Now back to the fovea. So if you take the human eye, this is the human eye. The central part here, or the optical axis, this is if you take the cross section. If you look at the optical axis, which is the blue axis in here, okay, that optical axis hit the retina, which is this surface, which is shown in here, hit it right at the center, and that center is called the fovea. Okay, if you take now this cross section and you try to see the photocells that convert the light into now, through a chemical reaction, into an electrical signal, into the neuron, to the brain, that, you take that, the distribution of photocells there, you'll find a really very interesting fact. And that is, we have 2 types of photocells in the retina. We have what we call the rods, responsible for low light imaging, night vision, to make it short, and the cones that you see here in black. These are the distribution. The cones are at the highest density in the fovea. And believe it or not, they have the highest resolution actually. They are smaller. Not only smaller, they are responsible of the reading, the color resolution. The rods, they are color blind photocells. The rods, they are actually motion detector. They detect motion. Okay, and that's why if you are a fan of astrology, if you go and look at the stars, you never gaze at the stars face head on. You gaze them obliquely. Like the star is here, you see there. Why? Because you want to use the low sensitivity, the low light sensitivity cells, which are the rods, to use them to detect those stars. So this is the distribution. So now the distribution of the fovea, as you can see, and I'm interested on the cones in here. Why? Because that's actually what I would like to use the images to be able to resolve the image at the highest resolution, at the best quality, but where? Only in the central part. The periphery here is not of my interest. Why? Because I'm looking exactly on this direction. That's why my interest is. That's where my gaze is. Okay? So that's basically the intelligence of the biology, but it's not there yet. This is a bit of history, so I'm not gonna cover that. But we'll come to that little by little. Okay, good. We get to the outline finally, but we'll go very, very quickly in here. I will not spend too much time there. We have 3 approaches in developing or implementing the intelligence. In here, the vision intelligence. We have the system level approach, we have the circuit level approach, and we have the device level approach, as I promised in the seminar announcement. Okay, we'll talk about each implementation level, step by step. We'll not cover all the aspects. Some of them, they are really interesting. They are shaded here, but due to the time limit, we're not going to cover them. We'll talk about the pyramidal CMOS image sensor. Well, I love, yes, the pyramids. These are an interesting architectural things, but they have a really interesting application in here. We'll talk about the architecture, physical design, scanning, and the dynamic range that is foveated. And that's where the implementation of the intelligence is done. The second level, which is circuit level, we'll talk about another level in which we will, and we will not spend too much time in here because of many reasons. Time is one of them. But in here, we'll try to develop the circuit level of the implementation of the intelligence using the multi-resolution some results. Then, last but not least, we'll talk about the device level, which is the current research activity. Okay, great. So, in the system level, what do? We try to enhance the dynamic range. And the dynamic range is basically the ability to see the bright and the low light levels at the same time. That's the dynamic range. The higher this range, the better, because you'll be able to see both informations. Okay, I will not take you to the details of that, but this is basically this approach based on a time domain in which we integrate multi-exposures, short and long exposures or long integration times. We fuse them and we build an artificial higher dynamic range. Okay, because you can do the dynamic range, enhance it both at the device level or at the system level by fusing the acquired image. So in this approach, what do? We keep the standard pixel, which is called the active pixel sensor. We keep the structure of that pixel the same. I will show that in a second, and we change the architecture. I'll show that in the next slide. So this is the classical array of CMOS image sensors, which is rows of pixels. We'll see the pixels in a second, and we scan row by row. Whenever we scan, we take one row, we dump it into sample and hold circuits in here, and we read them serially in here, okay? We read basically one row at a time. One-dimensional sampling. Not good. Why? Because the idea that we suggest in here, we suggest no. We are not going to read row by row. We're going to read ring by ring. So we will transform now the column bus through which we read the pixels output, not through the columns, no, but through the oblique columns in here, in 8 segments, which will enhance the speed of acquisition. Okay, in one aspect, we will not go into that details if because of the time, but we will read now in 2D. So ring, and then the next ring, and then the next ring. This is very similar to the iris, human iris. Okay, so that's the idea about the first idea at the architectural level. So this we call it pyramidal. Why? Because if you go on the pyramids, on top of the pyramids, and you look, that's the look of the pyramid, and that's why we call it pyramidal. So it's like you are looking at the pyramid from the top, and basically things are going in every single direction. Okay, this is the layout. This is the physical microscopic image of that. This is a cadence sketch. We just here show the buses. These are the signals. So this is one pixel, like shown in here. This is the pixel. So this is the photodiode, and these are the transistors. Okay. And what you see here in blue are the buses, which are oblique instead of being vertical like in the classical standard CMOS image sensor. The next aspect we want to do is the scan itself. As we said, we want to adapt the scan to our need, not to the display need, because we are trying to extract the information. That's the intelligence. Okay? So in the scan, in the classical scan, basically you row by row. You read this row, then you go to the next row, and so on and so forth. In the pyramidal scanning, what we suggest something called bouncing scan. This is called the rolling scan. Why? Because when you finish the last row, then you go to the first row, and so on and so forth. Why you do that? Because you want every single row, every single pixel to have the same integration time, which is the time to integrate the light. Okay? Good. For this one, no. For this one, you read. So this is a part of an 8 segments of the image sensor. Okay? And so in this part, you go from the center ring and you go to the outer ring. Like that, like that, like that. Now, each segment in here has its own sample and hold circuit. Okay? Okay, that's great. And these sample and hold circuits, we have 8 of them. They will read simultaneously these pixels. That means we can get up to 8 times the speed higher than the classical CMOS image sensor, but that's not the point that we're looking for. We are actually suggesting something new here. After we reach the last row or ring here in this case, we bounce back. So we read now the previous ring, and so on and so forth. So it's like you're going like opening the eye and then closing, opening and closing, opening, closing. What's the consequence of that? We'll see that in the calculation of the integration time. Mathematically, again, we are not going to go deep into that. We will find here at the bouncing edge, both at the first ring, as you can see here, the integration time of ring 1, this is the integration time of ring 2. You will find there is a very, very short period of time in here for that ring to be read when we bounce at that ring. And when we bounce at the outer ring, at the very last one, we will have also a very long time. Okay? We'll see. That will basically make the integration time not equal for every single ring. Maybe it's confusing. You will see these kind of images. These images have been acquired actually here at the University of Waterloo, in my office, in fact. These are Audrey Hepburn, if you know that, if you know her. So if you look at this picture, so this picture was acquired in the frame where the bouncing happened at the outer ring. So in this case, the outer ring has a short integration time, and then the integration time increases as you go to the center part. Okay? The next frame is actually the opposite, meaning the bounce happens at the center and goes back outwards. That means the integration time at the center is actually very short, and that's why there's no light to acquire or integrate, and then we have enough time to, integrate more light at the periphery. When you combine this and this, you get the normal picture, which is the uniform integration time. So all the rings will have the same integration time. Well, so what's the catch? What do we get from here? The catch is this. When you combine both frames, both pictures, you will get what we call the dynamic range or synthetic dynamic range in this case, in which basically the iron ring will exhibit a higher dynamic range than the other rings until a certain point where there's no enhancement of dynamic range. It's the same as the electrical dynamic range, and then it goes back up. This is the 3D cube. Okay, good. So what's next? The next is that we can play with the integration time, and we can make this crossing, not here, we can make it at the end, so that the bouncing, the integration time will basically be equal only at the boundaries, not before, as in here. And in this case, we can make the dynamic range foveal. Foveal means it's less dynamic range in the periphery and higher in the center part. Bingo. And that's the first implementation of the dynamic range. So the dynamic range now is given to the inner rings and less to the outer rings. And what does that mean? The dynamic range will or has to be translated into the bits for the A to D converter. Okay? So the A to D converter has to be higher bits, as you can see here, above 9 bits for the inner rings, for the foveal area, and the periphery we can use lower bits for A to D converter. So we are basically what? Compressing the data somehow. Or we are giving the resources to the inner rings and less resources. The resources means the A to D converter, which is, by the way, consumes a lot of power. Okay? Not only that, bits, I'm going to handle a lot of bits in here, but if I handle only for the center part and the others less, that's good enough. So here I'm trying to optimize basically the amount of data. I'm trying to maximize the transmission of the data over, maximize the information of the data over the data. Okay, so we're trying to maximize the information over the data transmitted. The second level, which is the pixel level or circuit level, in here I'm not going to spend too much of time. So again, here we said that only the region of interest, again like we did it before, but now we do it differently. We only get the region of interest or raw at the highest resolution. Now we are talking about spatial resolution. The other of less interest, we get them at the lower resolution. We'll show how. Okay, and the suggested idea now is called the multi-resolution. In this multi-resolution CMOS image sensor, now what we do, we opposite. We keep this architecture for sampling the image the same as the sensor, but we take the pixel and we play around with it. And that's why we call it pixel level. So this is a very the general description of the image sensor, of the multi-resolution CMOS image sensor. But here the addition is that we have to include these decoders. We call them multi-resolution decoders. Why we use this multi-resolution decoder on this side, and this side? It's because if you take a region here, which is this one, we basically decide like this region, programmably, somebody will say, I want this region with less resolution, meaning I just want the average of the information in here. So to do that, I developed a circuit that was actually copied by Micron at that time, and then becomes 80 now, and then up to now it becomes one semiconductor. I will show you that circuit. In that circuit, I basically charge share. I use charge sharing between the pixels in here to basically brush row and columns to make them all having the same charge value, and we make the averaging, and we just read only one out of this kernel. Okay. This is the pixel, the cadence. If you are familiar with cadence, this is the cadence view, a little bit complicated, and this is the pixel. In a very simple way, we have the photodiode in here, we have the shutter transistor in here that is responsible about transferring the charge from photodiode to a local capacitor, which is in this case a MOS capacitor. We have a reset transistor and the source follower amplifier in here, and these circuitry composed of just 4 transistors that will allow to make the charge sharing between this node and the adjacent neighbors. The control of these transistors is made through those multi-resolution decoders. Why? Because those, they can select 4 at that time, 4, 8, and 16 pixels at a time, and average them using this network of transistors, and at the end, we need only 1 pixel of them. Unfortunately, I don't want really to take too much of time speaking about this, but using this circuitry, basically, we will have not only single fovea, because we can have different places at the highest resolution where I don't do the averaging, and the regions that I'm not interested, I average them out. And at the end, we read only those of interest, not only one fovea, multifoveas, and the others we take their average. The device level, it reads itself, it needs a sub-outline. Okay? How we are doing, Dr. Fakhri? Almost
We
done?
still have few more minutes. Yeah.
Good, thank you. So, in this, which is the current research that I'm doing right now, we introduced a new concept, okay? We'll talk about the pain we are trying to address in a second. We'll talk also about the solution, the biomimicry strategy we used, and we'll talk about some of the fabrication, because now with this last component of the intelligence implementation, we'll talk now about the device. So we are going to talk about the device that we are discussing, and we conclude with 2 simple conclusions. Again, this is the anatomy of a CMOS active pixel sensor. So in here, basically, we have 3 major transistors. We have this guy, the amplifier transistor, which is nothing but source follower. We have the row select, which is responsible about selecting 1 row of pixels. And we have the reset transistor. Okay. The column pass transistor is not necessarily primordial to be put in the active pixel sensor, but some people they do it. Now, on top of this pixel, basically you have two things. You have the color filter, which is red in this case, meaning that